Welcome back. Suppose that I have a box here. The force of gravity, or the weight, acting on the box is 800 newtons down. I'm going to put here an XY frame whose origin is in the center of this ring. There are also three other forces acting on the box as shown here in the image. Let's call this one F1, but we don't know its value. But we know that this one is F2, which is 400 newtons, and this one is F3, which is 600 newtons. The angle here is 30 degrees counterclockwise. Then here we also have an angle that we call theta, and we can represent the direction of this vector like this. I'm going to draw a small right triangle here. Here you have 90 degrees. I'm going to put here 4, 3, and here I'm going to put 5. So this is another way to represent the direction of a vector. And keep in mind that the lines of action of all the force vectors, including the force of gravity vector, they all meet in the center of this ring. And now your goal is to completely counter this weight force with these three forces. Essentially what you need to have is this: force vector 1 plus F2 plus F3 plus the weight vector. It needs to give you a zero vector. You already have F2 and F3, both their magnitudes and their directions. And now you simply need to find F1 and theta in order to make this happen. Now this problem can be solved using the tools you have learned already. However, when you have to add more than two vectors, then it becomes cumbersome. There is an easier way to do it. Let me draw two coordinate frames that measure forces. Suppose that I have two vectors. This F2 vector with an angle of 30 degrees counterclockwise, and then I have this vector F3 equals 600 newtons, and we represented its direction like this. You could add them up using the triangle or the parallelogram law, but what you can also do is the following. You can decompose these two vectors into xy dimensions. So vector F2, whose magnitude is 400 newtons, and the angle 30 degrees counterclockwise from the positive x-axis, it can be represented differently as well using its xy components. So this component, F2x, well, that's 400 times cosine 30 degrees. That equals 346 newtons. And then F2y equals 400 times sine 30 degrees. So that will be 200 newtons. Similarly, F3 can be represented using its xy components as well. F3x equals minus 600 times, and then 4 over 5. And it's minus because it's in the negative x direction. So F3x equals minus 480 newtons. And then F3y equals 600 times 3 over 5, and that will give you 360 newtons. And this is positive because it's in the positive y direction. Now I can write it like this because let's say if you have some kind of angle here, let's say psi, then essentially cosine psi would be this ratio, 4 over 5. Or it would also be the absolute value of F3x over F3. I put the absolute value here because I don't want this minus sign here. Essentially you would have 480 over 600 here. And while the numbers are different, the ratios that you have here and here, they are the same. They are equal to each other. And so if you don't have this psi angle, if you have this format, then instead of cosine psi, you can right away put this one here. And then this one, 3 over 5, well, that's essentially sine psi, which is also f3y over f3, or 360 over 600. Again, the ratios here are the same. And so one way to represent vectors is using something called unit vectors. For example, there is a unit vector that is in the x direction, and we call it I, and then there is another unit vector in the y direction, and we call it j. A unit vector is a vector whose magnitude is always 1. So I equals 1 and j equals 1. Its purpose is to show direction. And so I can take this f2 vector and I can represent it like this. f2 equals 346 times I plus 200 times j. This one, that's f2x. Then this one here, that's f2y. Then this one here, it equals 1. And this one here, it also equals 1. Similarly, I can write f3 equals minus 480 times I plus 360 times j. Again, this one is f3x. Then this one, it's f3y. Again, this is 1 and this is 1. Note that I and j unit vectors are dimensionless. So here you have no dimension, nor here you have dimension. And the same thing here, the I and j unit vectors are dimensionless. And it makes sense because here you already have newtons, and here as well you already have newtons, and the same thing here, you have newtons, and here you have newtons. And so in the end, F2 also has newtons, and F3 has newtons. So I and j unit vectors must be dimensionless in order not to mess up the final units that we have here. In other words, the unit vectors don't contribute anything in terms of units. Essentially, I'm representing the same vector differently, but it's still the same vector. I can represent this f2 like this in terms of its magnitude and the angle, or like this in terms of its xy components. And the same thing here with f3, I can represent it with a magnitude and with some kind of angle. And if you really want to be formal, then according to the convention, the real angle that you have to calculate is the one that goes from the positive x-axis, but that's easy to calculate because if you know psi, then it's simply 180 degrees minus psi, and then you will get this angle. Or alternatively, you can represent f3 with a magnitude and then with this right triangle notation, 3, 4, and 5, but then you have to keep in mind in the back of your head that this vector points in such a way that it has a negative x component. But then you can also represent f3 like this, in terms of its xy components. I am simply representing the same information, but in a different form. That's it. And now you saw how to go from the arrow and direction notation to the xy component notation. We used trigonometry for that. But what if you want to go back? What if you have this notation, but you want this notation, where you have the magnitude and the angle? Well, that's quite easy actually. If this is your f2x, and this is f2y, then you can simply shift this f2y like this, and then you have a right triangle here. So you have 90 degrees here, and that's your f2. So you can compute the magnitude of this f2 vector like this. Square root f2x squared plus f2y squared. Essentially, I'm using the Pythagoras theorem here, because this is a right triangle. And if I do that, then I will get 400 newtons. And now, in order to get this theta angle, I do the following. I know that tangent theta equals f2y over f2x, because this f2y, it's also this one here. So you can form tangent theta like this. And so theta simply equals inverse tangent and then f2y over f2x. And that would give you 30 degrees. However, you have to be careful here. Again, I have my coordinate frame, xy, and imagine that I have this vector. Let's just call it f. In this case, both components are negative. This is fx, and this is fy. If you write inverse tangent fy over fx, then even though they're both negative, these negatives will cancel each other out. And so in the end, what you will get is this angle here. Let's call it alpha. However, you would like to get this angle. Let's call it theta. This angle theta goes from the positive x direction. In this coordinate frame, we have 4 parts. Part 1, part 2, part 3, and part 4. These parts are called quadrants, and so this theta angle will tell you in which quadrant you really are. In this case, you're in the 3rd quadrant. If you get alpha, then you might think that your vector is here and alpha is here and you're in the 1st quadrant. But that would be wrong. If both of your components are negative, then in order to get theta, you have to add 180 degrees to alpha. Now in Python, there is a function called atan2 and then parenthesis, and this is for arctangent, but then if you have 2 here, then it will take into account the signs of the components, and then it will give you the right quadrant. Note that this right quadrant can be obtained in 2 ways, either with this theta angle or with this beta angle. It's just in case of theta, you go counterclockwise, and in case of beta, you go clockwise. In other words, if you go in this direction, then your angle is positive. If you go in this direction, then your angle is negative. So let's say if alpha equals 30 degrees, then theta would be 180 plus 30, which is plus 210 degrees. Or alternatively, I can say that beta equals minus 150 degrees. So you would have 180 degrees minus 30 degrees. That would give you 150 degrees, but because you go clockwise, it's actually minus 150 degrees. Also note that vectors are formally denoted like this. For example, f2 and the arrow. And we usually use this notation when we represent our vector in this form, using the unit vectors. But now when we calculate the magnitude of the vector, or the length of the arrow, which in this case is 400 newtons, then vector magnitudes are formally denoted like this. f2 arrow and then the absolute signs, and then that would be 400 newtons. And then you could also add 30 degrees counterclockwise. And then, like mentioned before, this notation we would normally use if I want to express this vector in this notation, using the unit vectors. However, many times throughout this course and in general, instead of representing the magnitude like this, people take a simpler route and simply represent it like this. F2 equals 400 newtons and then 30 degrees counterclockwise. So just know that in this course, when I represent my vector like this, and I simply write F2, then I mean the magnitude, because I don't want to write those arrows and absolute signs all the time. And if I include an arrow without absolute signs, well, that I normally reserve to this kind of notation. And finally, what I want to mention is that in both cases, either we use this notation using the unit vectors, or this notation using the magnitude and the angle. In both cases, you're representing information about your force using 2 dimensions. It's just, in this case, your one dimension is the x dimension and another dimension is the y dimension. And then in this case, your one dimension is the magnitude of the vector, and then another dimension is the angle of the vector. Again, it's just I'm representing the same information but in 2 different ways. It's like if you have an address, let's say you live somewhere in a house, I can either represent your address using the street name, the house number, the apartment number, your zip code. With this information, I will be able to find your house. Or I can represent your address like this, with longitude and latitude coordinates. In both cases, I will be able to locate your house on this planet. And now you might ask, why do I need this unit vector notation? Well, it turns out that it's a lot easier to add vectors like that. Again, let's take F2 and F3. And so if I want to add them, then I can do it very easily using the unit vector notation. And that's why I'm putting the arrows here now. So this is the F2 vector plus this is the F3 vector. And now what I need to do, I need to add their I components first and then their J components. And so I will have I 346 minus 480 and then plus J 200 plus 360. And then I will get minus 134I plus 560J. So that's the sum of these 2 vectors. And let's say that now I want to go to that other notation where I have the magnitude and the angle. First of all, let me draw this XY coordinate frame that measures forces. So the x component of the sum is minus 134 newtons. The y component is 560 newtons. Using the parallelogram rule, I can add these components up. So this is my F2 plus F3 magnitude. I have a right triangle here. And by the way, I should not forget the units. So the sum of these 2 force vectors is also in newtons. And so the magnitude of F2 plus F3 equals square root minus 134 squared plus 560 squared. But note that since I'm squaring this number, minus 134, this minus sign is unimportant here. So I can also just write this thing like this. 134 squared plus 560 squared, and that's my magnitude, 576 newtons. And as you calculate this magnitude, now you can mathematically see that your magnitude can only be positive. It cannot be negative. Because even if you have negative components here, you square them and they become positive. So your final answer can either be 0 or only positive. And obviously, you have a 0 magnitude only if both of your components are 0 newtons. So we have the magnitude, but what about the angle? Well, we would like to get this angle. Let's call it theta. And so what we can do first, we can calculate this angle alpha. That's simply alpha equals inverse tangent 560 over 134. That will give you alpha. And so theta equals 180 degrees minus alpha, and it will be 103 degrees. And that's another advantage of this unit vector notation. Or I can also call it Cartesian vector notation. So when I say a Cartesian vector notation, I mean this notation, I and J. And so another advantage of this Cartesian vector notation is that here you don't have to worry about the quadrants on this xy plane. This unit vector notation will tell you right away in which quadrant your vector is. If you see that you have a negative x component and a positive y component, then you automatically know that you are in the second quadrant. And so that's the result. That's the addition of f2 plus f3. You would have also gotten it if you had used the triangle law or the parallelogram rule. However, when you have to add or subtract many vectors, then it's a lot easier to do it using this unit vector notation. If you want to subtract vectors, then it's like this. f2 vector minus f3 vector, that's your f2 vector, minus, that's your f3 vector, and so all that equals, first of all, I subtract the I components, 346 minus 480, and then plus j, 200 minus 360, and so that equals 826i minus 160j. And then you can get the magnitude and the direction of the vector in the same way. You use the Pythagoras theorem to get the magnitude. You see that you have a positive x-axis but a negative y-axis, so you must be in the fourth quadrant, and from that you can calculate the appropriate angle, either going counterclockwise where your angle will be positive, or going clockwise where your angle will be negative. And so, using this unit vector approach, try solving this box exercise yourself. Remember, you have f2 and f3, and you have to find f1 and theta in order to completely counter this weight. So you have to have this situation here. A zero vector simply means that all the components in that vector are zeros. So the zero vector, it really means 0i plus 0j. That's what it means. So good luck with doing this exercise by yourself, and I'll see you in the next video. Thank you very much. Welcome back. Let's now solve this box problem. In order to completely nullify the force of gravity or the weight vector, the resultant vector that you get when you add up f1, f2, and f3, it has to have the same magnitude that this weight vector has, but it has to be opposite in direction. It has to point up in the positive y direction. In other words, using the Cartesian unit vectors, if I say that my weight vector is 0i minus 800j newtons, then f1 plus f2 plus f3, which we can call fr, the resultant vector, it has to be 0i plus 800j newtons. Then fr vector plus the weight vector, it will be I times 0 plus 0 plus j times 800 minus 800, which will give you 0i plus 0j newtons. And so first of all, what we can do, we can take this f2 vector and we can represent it using the unit vectors. It's 400 times cosine 30 degrees and then I plus 400 times sine 30 degrees j. And then f3 vector equals minus 600 times 4 over 5 I plus 600 times 3 over 5 j. And of course, they are all measured in newtons. Now we have to find f1 and theta. What I want to do, I also want to take this f1 vector and represent it using the unit vectors. So what I will do first, I will define another angle here. I'm going to call it alpha. You would agree that alpha equals 90 degrees minus theta. And now I will have f1 vector equals F1 magnitude times cosine alpha or cosine 90 degrees minus theta, and that's in the I direction, and then plus F1 sine 90 degrees minus theta, and that's in the J direction, and newtons. And so you know that if you add up all the I components of these three vectors, then you need to get 0. And if I add all the J components together, then I need to get 800. And so let's do that. In the I direction, I have all this, which equals 0. I've simply added up these three terms that must give me 0. And now, if I do the same thing with the J components, then I need to get 800. And so for J, this is how it looks like. So essentially, I have two equations and two unknowns, theta and then F1. If I rearrange my first equation, then I will have this thing, F1 times cosine 90 degrees minus theta, and all that equals 133.6. So I left the first term here, and then everything else went to the other side of the equation sign. I can do the same thing with J. This is the first term, then you have 800, which is this one here, and then all the other terms will go to the other side of the equation sign, and that will give you 240. Now in the first equation, you can write F1 equals 133.6 divided, and then this thing here, it will go here into the denominator, so I will have cosine 90 degrees minus theta. So that's my F1. And now I can take this expression for F1 and I can put it here into the second equation. And so my second equation will be 133.6 divided cosine 90 degrees minus theta, that's instead of F1, times sine 90 degrees minus theta, and that will equal 240. Now in general, when I have a right triangle here, and then here I have A, B, and then C, and then angle, let's say phi, then you know that sine phi equals B over C, and then cosine phi A over C. So sine phi over cosine phi, that's B over C divided A over C. In other words, it's B over C times C over A. So the C's cancel out. And so you will have B over A. And what is B over A? Well, that's tangent phi. So sine phi over cosine phi, that's tangent phi. Which means that in this equation, sine 90 degrees minus theta divided cosine 90 degrees minus theta, that equals tangent 90 degrees minus theta. So your equation here then becomes 133.6 times tangent 90 degrees minus theta, and that's 240. And so I'm going to continue here. Tangent 90 degrees minus theta, that's 240 over 133.6. It means that 90 degrees minus theta equals the inverse tangent of this ratio, which gives you 60.9 degrees. That's 90 degrees minus theta. It means that theta equals 90 degrees minus 60.9 degrees. That's 29.1 degrees. So that's your theta. And now that you have your theta, you can plug it in here and you can compute your F1. Let me do it here. F1 equals 133.6 divided cosine 90 degrees minus 29.1 degrees. and that will give you more or less 275 newtons. More precisely, 274.7 newtons. And there you go, you have your F1. Your theta was 29.1 degrees, that's your theta, and your F1 is 274.7 newtons. And there you go, you have found your F1 and theta, and now the sum of all of these three forces, F1, F2, and F3, they will completely counteract this force of gravity. Thank you very much. Welcome back. So we have solved this box exercise, but in this video, I want to mention something very quickly. Look at how we set up our problem. The line of actions of all the vectors go through one point in the middle of the circle. That's why, even though the box has a considerable size, we can still treat this problem as a particle equilibrium problem. We can just take that point in the middle of the circle and apply all the forces to that point. That point is our particle, but that's only possible because the lines of action of all the forces go through that point. But now imagine that you have this configuration for the box. Your ring is here. This is your weight force. It acts on this point because this point is the point of center of gravity. And now these are your three forces. And now the line of action of the weight vector does not go through this point in the middle of the circle. That means that if this is your FR that you got by adding up these three forces, then there is a distance between the lines of action of FR and the weight. And that distance is perpendicular to both FR and the weight vector. That mismatch will make the box rotate. Just like force makes objects accelerate, and then mass, it's actually resistance to acceleration, there is something that makes objects accelerate angularly. So the units for acceleration are meters over second squared, but the units of angular acceleration is radians per second squared. Just like with acceleration, you got it by taking the derivative of velocity with respect to time, and that's why you had meters over second divided by second, which gave you meters over second squared. The angular acceleration is the derivative of angular velocity with respect to time. Angular velocity tells you how fast something rotates. For example, a wind turbine can rotate 10 radians per second, for example, and that would be your omega. And if you take the derivative of angular velocity with respect to time, then in terms of units, you have radians per second over second, and that will give you radians over second squared. And then this I here, that's called mass moment of inertia, and it's resistance to angular acceleration. And so just like force makes objects accelerate, there is something called a moment that makes objects accelerate angularly. And when you have this kind of situation where you have one force vector up and another force vector down, and then you have perpendicular distance between them, that introduces a moment. In this particular case, this moment equals Fr times d, or W times d. It doesn't matter because they have the same magnitudes. And this moment will make this box accelerate angularly. And to stop the box from rotating, you need to have a counter moment, which has the same magnitude, but which is opposite in direction, which means that moments are also vectors. So let's say that you can represent a moment like this, and so the moment vector would be then perpendicular to the plane of rotation. So this is your plane of rotation, and the moment vector is perpendicular to that. If you have it in another direction, like this, then the moment vector points in the opposite direction, it points down. But again, it's perpendicular to the plane of rotation. Or let's say that your moment is like this, then your moment vector would be like this. Again, perpendicular to the plane of rotation. So as you can see, it also has a magnitude and a direction. And so when you also need to consider moments, then these kind of problems are called rigid body equilibrium problems. And we will treat moments and rigid body equilibrium problems later in this course as well. But for now, just know that in particle equilibrium problems, you don't have moments because the lines of action of all the force vectors go through the same point like I showed you with this ring. In this configuration, there is nothing that would make the box accelerate angularly, and that's why it's a particle equilibrium problem. If you have something that makes the object accelerate angularly as well, then it's a rigid body equilibrium problem. And finally, a good way to determine the direction of your moment vector is to use the right-hand rule. So here, for example, if you take your right hand and you curl your fingers like something would rotate, so you would curl your fingers in the direction of your rotation, then your thumb will point up. So in this case, your right hand thumb would point in the direction of the moment vector. These are your knuckles here, which means that on a 2D plane, you can represent moments like this. You have this rotation arrow, but that means that the moment vector actually points into the screen according to the right-hand rule, because that's where your right-hand thumb would point. And in this case, your moment vector points out of the screen towards you, and also your right-hand thumb would point out of the screen towards you. So we're going to leave the moments alone for now, because we still have to work with forces, but we will get there later on in this course. Thank you very much.